In this last segment of the wave introduction, we will be zooming into slightly more difficult concepts of waves, especially the use of the wave equations V equals to F lambda. So let's start. Okay, what is the relationship between V equals to F lambda? Okay, the period, wave speed, frequency, and wavelength. Okay, we know that wave can travel into different mediums. Okay, what do I mean by different mediums? For example, it can move from solid to liquid, liquid to gas, or it can move from like shallow water to deep water. Okay, the medium, okay, the liquid, solid, or gas that it moves through can change, and whenever waves move in different medium, okay, the speed of the wave changes. The speed is dependent on the medium in which the wave is traveling. So its speed in the new medium can be higher or lower. And when the speed changes, okay, the wavelength will change because the frequency of the wave will not change. The frequency of the wave will always remain the same, okay, as long as you don't change the source of disturbance. Okay, the source is the one that is producing the wave, the disturbance. Okay, so the how do I know it? Because I use the formula V equals to F lambda. Okay, so I'm going to write down over here. So we have learned about the formula V equals to F lambda. Okay, so V is dependent on the medium. Okay, the solid, liquid, gas, or the deep water, shallow water will affect the speed. Frequency is always dependent on the source or the source of disturbance. Okay, usually will not change, and the wavelength is dependent on the speed. Okay, so if the speed increase, the frequency is the same, then the wavelength would also increase. Similarly, if the speed decrease, then the wavelength would also decrease. Okay, so you can take a look at here. I have a wave in the first section. I am moving through different medium, okay? So the wave in the first section looks like this. And then after I pass through this dotted line, I move into another medium. Okay, it's not stated what kind of medium. It can be from a liquid going into a solid, or it can be from a solid going into a liquid, or a solid going into a gas, or it can be from a deep water to a shallow water. But as long as there's a difference in the medium. So in the first segment is one medium, then in the second section, I'm moving into another medium. Okay, what you will notice is that the wavelength change. Okay, from the graph, I can see the wave. I can't see the speed immediately, but what I can see over here is that the wavelength change. Okay, so the wavelength originally was in the first section, the wavelength was this distance. Okay, I choose the trough to the trough. This is the wavelength. Okay, now my wavelength has decreased. It becomes this distance. Can you see that it's become shorter? Okay, not only does the wavelength change, the amplitude also decreases. Okay, usually the amplitude decreases the further away you get from the source. So the source of vibration is over here. The further and further you get, because energy will be absorbed by the medium during transmission. It will be absorbed, some of the energy will be absorbed by the particles. So it will get lesser and lesser and lesser energy, and therefore the amplitude will decrease. The amplitude is linked to the amount of energy that the wave has. So the energy will get lesser and lesser and lesser. Okay, so you can see that the wavelength actually decrease. So if the wavelength decrease, okay, the frequency is the same. So we use the formula V equals to F lambda. Okay, you will get that the velocity will also decrease. Okay, the velocity will also decrease. Okay, sometimes they will not give you the wave, they will give you wave fronts. So if it happens in the form of a wave front, then it will look like this. Let me erase this. Okay, so sometimes they will not draw for you the wave, they will draw for you the wave fronts, which looks like this. Drawing below. Okay, so I use the crest. Okay, so these are the wavefronts. Okay, I draw the wavefronts on all the crests of the wave. So again, between two wavefronts, there is one wavelength. You see that wavelength has decreased. Okay, so they were not drawing the wave for you, they will draw the wavefronts, possible also. Okay, so by comparing the wavelength in the second section to the first section and applying the formula V equals to F lambda, we can deduce that the speed becomes smaller in the second section because the wavelength has decreased. The waves are nearer to one another, or the wavefronts are nearer to one another. Okay, so the answer is as follows. Frequency is the same. Okay, because we did not change the source. Okay, and then the wavelength is shorter. So based on the equation, shorter wavelength, the speed of the wave will be smaller as well. Okay, and then one thing that you need to know, you need to memorize is the difference between deep and shallow water. Okay, you need to know that the wave speed is actually faster in deep water. Okay, how do you remember it? You try to remember in the deep sea, the water moves very fast as compared to actually slows down, okay, because it's shallower. So as the water moves from shallow to deep, okay, the deeper part, the speed of the wave increases. Okay, this one you must know. Okay, remember deep sea, the water moves very fast. Okay, so the speed of the wave would have increased. So if you were to use the formula V equals to F lambda, what can you deduce about the frequency and the wavelength? Again, change as the wave moves into deep water because it's still the same wave. Okay, so frequency is the same, the source is the same. Okay, but as the speed increases, then the wavelength would also increase. You will see that the waves are not so closely packed. Okay, the wavefronts are further apart. The wavelength of the wave will be greater in the deeper sea. Next type of questions. Okay, I have a displacement distance graph. So these are the different particles at a particular timing. So I have particle P, particle Q, particle R that is on this wave. Okay, this is a transverse wave. Then they ask you determine the direction of movement of particle P, Q, and R in this transverse wave. So I give you that the wave is moving towards the right. How do I know P, Q, and R? How are they moving? You know it's a transverse wave. So if the wave is traveling in this direction, the particles P, Q, R cannot move in the same direction as the wave. They must move perpendicular to the wave on the spot to vibrate up and down, up and down, up and down. But I do not know how is it moving, whether it's moving up or is it moving down? So how do I determine whether it's moving up or moving down? I need to draw at the next instant, how will the wave looks like? So I'm going to draw, okay, since the wave is traveling to the right, I just draw the next instant where the wave moves to the right. How much to draw? Just draw by a little bit. So I'm going to start from here. So I'm going to draw the blue line. Okay, so instead of starting at 0, I start at maybe 0.5. Okay, so I'm going to draw the entire wave up to the same amplitude. Okay, can you see my entire wave? I just shift my entire wave to the right. Oh, hang on. Okay, I just shift my entire wave to the right. So now my entire wave is the blue line. Okay, so how is the particle moving? Okay, let me use another color. So let me use brown. So particle P, okay, and here now the next instant I'll move to the blue wave. So I'll be moving downwards. Q will be moving upwards. Okay, because Q, the next instant will be on the blue line, so it's moving upwards. And then R, the next instant, will be moving downwards. Okay, so P is moving down, Q is moving up, and R is moving down. Okay? Okay, Next one, slightly even more difficult question. A wave in a string is traveling to the right. Okay, so the wave is traveling to the right. The speed is at 2 meters per second. The diagram shows the displacement distance graph at t equals to 0 seconds. So at a particular instant when the time is 0, I take a photo. I have many particles. P, Q are one of the particles, okay, inside those waves. So this particles is like that, is moving to the right at a speed of 2 meters per second. Sketch the graph to show how the wave will appear 3 seconds later. Okay, so 3 seconds later, how will I know what will happen to it? Okay, I couldn't just anyhow sketch. Okay, I couldn't just like say, hey, I start from here, then I sketch. Okay, it cannot be like this. So I need to do some calculation. I give you the speed, and this is a displacement distance graph. So I could get the distance. The distance is actually the length of one wave, while I could get the wavelength. Okay, so one wave, this picture exactly show one wave. So the wavelength is actually 8 meters. So I'm going to apply the formula V equals to F lambda. So I sub in, my speed is 2 equals to the frequency I do not know times the wavelength 8. So I get my frequency is 1/4. Okay, so I'm not interested in frequency. I'm interested in period. I want to find the time taken for one whole wave. Okay, so from there, the frequency is 1/4. The period will be 1/1/4, which is 4 seconds. Okay, so what does it mean that? It means that the period of the wave is 4 seconds. It takes 4 seconds to generate one complete wave. Okay, the next thing that you must know, each particle during a wave, it will always move in 4 different segments. The movement is always 4 different segments. Okay, so if 4 different segments come back to its original position, and then it will repeat itself again, 4 different segments back to its original position. So if I have the period, the time for one wave is 4 seconds, that means for each segment within the wave, I have 4 segments in one wave. So within one segment, I will take 1 second. Okay, so I first sketch how does this next instant looks like. Okay, so I'm going to sketch. Okay, so I'm only going to look at P and Q. P will be moving downwards. And then Q will be moving upwards. Okay, so what do I mean by the 4 segments of a wave? Okay, so let's just look at P. Okay, I'm going to sketch at the side over here. What are the 4 segments for P? Okay, so P is at the top. To have one complete cycle, how would P move? I would move 4 segments. The first segment down to the rest position. 1. Oh. Then I will continue to move down again. 2. Then I'll move up. 3. And then I 4th segment, I'll move back to my original position for particle P. Okay, after one complete wave, I should always move back to my original position. So if P, my original position is right at the start, after the end of one whole wave, after the 4 segments, I should move back to my original position. So P is at the highest point already, it will move down, down, up, up, 4 segments. Okay, that's for P. Okay, so 3 seconds later will be I have moved 3 segments. So P will have moved down, down, up. So then at 3 seconds later, P would have been at here. Okay, at the equilibrium position over here, the new P. Okay, next let's take a look at Q. Okay, let me use another color. Let's use green over here. Okay, so Q, let me just draw over here. Okay, Q is originally at the rest position. Okay, so after 4 segments, I must go back to the original position. So I need to know Q is moving up or down first. So I have already drawn the next instant, Q will be moving up. Okay, so the next instant, Q will be moving up. So this is 1 segment, then go down, 2, 3, and 4. Okay, so I'll go back to my original position. So 1, go to maximum, then go down, down, and up. 1, 2, 3, 4. At 4, I go back to my original position. Then I'm going to repeat again. 1, 2, 3, 4. Okay, I'm going to move up, down, down, up again. The next cycle. So again, 1 cycle, 4 segments. After 3 seconds, I will be at the bottommost point. So I will be at here. 3 seconds later, I will be at the bottommost point. So if I were to do a sketch, my graph will look like this. 2 to 4 will be going like this. 4 to 6 will be going like this. 6 to 8 will be going like this. So I will just continue with my path. Okay, so just based on 2 particles, I will be able to sketch what happens at 3 seconds and draw and label the position of P and Q. So P will be at the equilibrium position and Q will be at the lowest position. So this is the answer. P equilibrium, Q will be at the lowest position. This is how I get it. After 3 seconds, after 4 seconds, which is 1 period, okay, P and Q will be back to its original position. The wave cycle will be, the waveform will be exactly the same again. Okay, what happens if it's 2 seconds later? Okay, so let me just draw in a 2 seconds later. 2 seconds later, so the period is 4 seconds. One whole cycle takes 4 seconds. If I want after half a cycle, 2 seconds later, everything will be in the exact opposite direction. Okay, so your P is the crest. Now your P will be at the trough, and then your Q will still be at the equilibrium. Okay, and then this one is your trough. It will become your crest, and then this one will be at equilibrium. So it will be exactly opposite like that. At equilibrium, it will still remains at equilibrium. Okay, because exactly opposite of it is still at equilibrium, but at the crest will become the trough, and then the trough will become the crest if it's exactly at half the period. Okay, and if it's at 3/4 of the period, 3 seconds later, then you need to go and count 1, 2, 3 and see where it ends off. Okay, you may scan the following 2 QR codes to work on more practices as well as crossword puzzles. Okay, and that's it for the end of this chapter.